Hi. So, my name is Pau Amaro Sevane, and this is intended to be, I hope, there will be a series of lectures which will provide you with with a mathematical background, which I deem necessary for you to understand general relativity from a geometrical standpoint. For that, we're going to go through many different topics, which I will define through the lectures. But in any case, we want to start with analysis 1. I will be mostly using the book by Terence Tao, because I think it is an exceptional book which will allow you to understand analysis. You probably know analysis, meaning that you know how to use analysis to achieve different goals. But what we need, or at least what I intend to do, is to teach you analysis in such a way that you understand analysis and you don't just use it as a tool, but you understand what you're doing. This is important because in order to understand topology, we need to understand, I have to introduce to you the concepts of limits, in particular lim sub, lim inf, and etc., and so on and so forth. I'm going to again follow very closely this book here. Well, it's no, it's not mirrored, by Terence Tao, of course. Okay, so of course you can take the book and read yourself, but I am making these summaries not just for the sake of wasting my time, which is a very honorable thing to do, but they are meant as a kind of summary for a group of PhD students who are following my lectures. They have asked me to do some summaries based on our lectures, and this is what I intend to do. So in this series of first lectures, as I was saying before, we're going to start with analysis. So there we go. So following the book by Tao, I'm going to start right at the beginning. So what are the natural numbers? Take into account that we're really going from the natural numbers. So the goal is to really go from the natural numbers up to general relativity. And again, I will approach general relativity from a geometrical point of view, so that we need to introduce topology, differential geometry. And I think that a very natural way to do that, to understand how to mathematically introduce these concepts and to understand them, is by using analysis. So I want to start with the natural numbers. Of course, you already have, unfortunately, I might say, hardwired in your brain what the natural numbers are, right? They just live in line and they are separated regularly. Okay. But for instance, why is it true that 3 times 2 plus 5 is equal to 6 plus 15? Why should A times B plus C be equal to A times B plus A times C? this is a very fundamental property which can be derived, be proven for more primitive and even more fundamental properties of the number system. Now, some of the statements that we're going to have, that you're going to face, are going to be obvious for you. But the most important goal probably that I want to achieve by going back to the natural numbers is that you start from a tabula rasa. So you just delete everything you have in your head, so to say, so that you can have a new look at what numbers are and why we introduce them the way we have introduced them. Okay, so we are going to start with the natural numbers, n, but we will follow with the integers, z, the rationals, q, and the real numbers, r. Now, all the number systems, for instance, the complex numbers, but we will address them much later. Now, again, we are going to at least try to understand what these numbers are and how they have been defined. For instance, y is 0, 0, 1, 2, 3 equal to 1, 2, 3, but 1, 2, 3, 0, 0 is not 1, 2, 3. Also, as I was saying before, why can we do this kind of things? Or why a plus b is equal to b plus a. This might sound to you as a joke, but it is not a joke. And the way that Tao in his book introduces the natural numbers is a wonderful way to move ahead, to move forward, and have a look, a deep look, at least, let's say, a deep beginner's look at that set theory. You will see that there is a very clear parallelism between the way we introduce the natural numbers and that set theory, or at least axiomatic set theory. In particular, we will work upon a construction, and that construction has as building blocks some things which we call the axioms. So, axioms. Now, a few words about this. When I was at high school and we had algebra, we had to prove this and that theorem, etc. I had a very peculiar problem because I did not understand axioms. I would usually get stuck at the axioms and I could not move forward. Why is this person introducing this kind of axioms? Why, in order to define a set, a group, or whatever, do you need axiom 1, 2, 3, 4, or whatever axiom? What would happen if I cancelled out axiom 3? What would happen if I replaced axiom 2 with a slightly different way, with a slightly different axiom, a very similar one, but a slightly different one? And this would lead me to an infinite loop in my brain, which did not allow me to move forward. And while my classmates were already solving the exercises of chapter 1, chapter 2, chapter 3, I was stuck at the axioms. And since I hope that I am not the only human being on Earth who has this problem, I have decided that it would be nice for whoever has the same proof as I had in the past to say a few things about the axioms. So an axiom is a kind of, if you want, social agreement. So we have a few people working on something, and we want to develop a theory about something. And in order to define that theory, we must have a playing ground, if you want. We need something to build upon it. We need to work on something common. So we must agree on a series of rules. So, for instance, one of these persons over here says, do you agree that, I don't know, a natural number is an element in the set 1, 2, 3, 4. This person here is asking that question, and the rest of them say, yes, it seems logical. Now, this example probably is a little bit counterintuitive and not very useful, because I told you that I want to build up the whole natural numbers departing from zero, from the absence of everything. But we could agree on something which is logical, is clear enough so that all of us understand it, and cannot be reduced to any even more primitive statement. All of us agree on it, and we say yes. We think it is a very logical thing, and we want to just accept it. When I was studying, my friends would say, don't just think about it. It is a truth which you cannot prove, and you have to move forward. But I could not do it because of the problems that I was mentioning before. It took me some time to understand that an axiom, while it is true that it must be envisaged as a truth which you cannot prove, I was lacking an element, and the element is that it was not a dictator who imposed axioms 1, 2, 3, 4, and 5, or whatever. It is a logical thing which seems reasonable to believe, and all of us have to agree on it before we can move forward. That's an axiom. Now, the natural numbers can be built in terms of the Peano axioms. We will move slowly forwards, step by step. So, how are we to define what these numbers are? Okay, we would start with a definition by saying that, look, a natural number is any element of this set, and please notice that I have not defined what a set is. 0, 1, 2, 3, etc. I must say that natural numbers are sometimes also known as whole numbers, because I am taking also into account 0 here. Some authors do not take it into account. Okay, so it looks like we have solved the problem. A natural number is any element in this set, right? Yeah, maybe. But it's asking you to assume something which you don't understand. This definition of, okay, look, start here at 0 and jump forward indefinitely. It's not quite acceptable, right? Because we have a problem here. Who is telling you that this sequence of numbers is not ill-defined? You could have problems. You could, start jumping from 0 to 1, from 1 to 2, from 1 to 3, etc. But at number, say, for whatever reasons, instead of moving to the, let me see, to the 12,854,659, you would jump back to 3. You say, probably. That cannot happen, because I know that the following one is the previous one plus 1. Well, you don't, because I have not defined it, and that you didn't either. The only thing we have defined is this series of jumps moving forward. I have also not defined how to jump forward. So we could have a problem of being resetted, going back to 0, or going back to, say, the previous number, which is 57, or going back to 3. That's a very difficult problem. It is, as a matter of fact, a very tedious and boring thing to do, because you would have to move forward, starting by 0, all the way up. But again, we have not defined what is to move forward, and we have to make sure that you are not going to be, wrapping up and going back to 0 or whatever. Okay, so we need to find out a way, a scheme to avoid this. The way we have introduced natural numbers looks like we want to say that they are 0 plus everything which can be obtained from that number by incrementing. So that if we use n++ to denote the increment or the successor of n, then, for instance, 3 is defined to be 4. And 3 is going to be, sorry, I didn't mean that. 3 will be, of course, 5, right? Now, we define this notation to the jumps that I was referring to before. So we are moving forward, and we are departing from 0, so that we have a system in which 0 is the starting point, and then it follows like 0 plus plus, 0 plus 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 plus, and so on and so forth. Okay, now let's identify right now the two most important elements that we are making use of. The two most important, and actually the only two elements, the only two notions that we are making use of. first one, and that's going to be our first axiom, axiom 1. I'm going to assume that 0 is a natural number, and that notation means that 0 lies in the set of natural numbers. But you can write it down with words, of course. 0 is a natural number. And again, this is an axiom. I am not imposing that axiom on you. You and I, we are agreeing that it makes sense. I cannot prove to you, actually, I'm not going to go into details, but for these lectures, I'm going to assume that I cannot prove to you that 0 is a natural number. But you and I, we agree that it makes sense to define it as a natural number. And we're not going to ask the question in 2 hours whether 0 is a natural number or not. We have agreed upon it. 0 is a natural number, full stop, because it makes sense. All right, so this is the first thing we need. What is the second thing? Well, we have implicitly assumed, and since you have not protested, and you cannot protest because this is a recorded video, we have agreed that if n is a natural number, then its successor, n++, is also a natural number. I was joking before, you cannot protest because you cannot talk to me right now. But during my lectures, usually, no student protests because you are used to implicitly assume these kind of things. I'm just stating them right now, here, loud. Okay, so that's going to be our axiom number 2. If n is a natural number, then n++ is also a natural number. Okay. So these two axioms now allow us to introduce definitions and propositions. For instance, we define 1 to be the number 0++, the natural number 0++. We define 2 to be the number 0++, and so on and so forth. By the way, here I am using this semicolon and equal symbol to denote that one thing is defined to be equal to the other thing. Okay. So, as an example, I ask you to now prove that 5 is a natural number. You should be able to do it by yourself. And whenever you see this symbol, it means that I am asking you to prove it by your own. Okay. So, with the two first axioms that we have introduced, we start to be able to develop something. But we still have that issue about wrapping around or being reset. How could you possibly avoid that? And this is actually not fiction. This happens when you are using a computer. For instance, consider a number system which is made by the numbers 0, 1, 2, and 3, in which the increment operation goes back from 3 to 0, so that 0++ is 1, 1++ is 2, 2++ is 3, but then 3 plus plus goes back to 0. Well, this would be a big problem. And the way we have previously introduced as a kind of, first definition, an informal definition of what the natural numbers are, could have this issue, and we want to avoid it. How could we avoid these kind of things? Well, you and I agree that it makes perfect sense to introduce another axiom, the axiom number 3, which solves this issue. If you want, you can press now pause and try to think about yourself how this axiom would look like to avoid the wrapping up issue. So, I'm going to say that 0 is not the successor of any natural number. So for every natural number n plus plus cannot be 0. Now, you see that this axiom would make sense, and again, I am not imposing it onto you. You could, come up with a different way of doing it, but I would be very curious to know what that other possibility could be. We solve the problem of being, wrapping up or being reset to 0. Now, thanks to this, you can now prove that 4 is different than 0. Now, we have been talking now for about 27 minutes, and you see what is going on. If I had explained to you right at the beginning of this video that we would be doing this kind of exercises, you probably would have thought that I have an issue. Why would I care? Or why does this person care that 2 is different than, for instance, 0? Sorry, that for instance 2 is different than 0. It is obvious that 2 is different than 0. Well, you now know that it's not trivial. Okay, so it's up to you to prove it now. Now you are in the condition of proving it. So we have now solved the problem of about being wrapping up and going back to 0. But we still have the problem of being pushed back, if you want, at the previous number. Consider now the series of sorry about that, it was some ad. Consider a number system of 5 numbers, like say 0, 1, 2, 3, and 4, such that the successor at some point is hitting a maximum at 4. In this way, or in this world, 0 plus plus is 1, 1 plus plus is 2, 2 plus plus is 3, but 4 plus plus is 4. So we're being resetted. We're wrapping, if you want, we're wrapping back to the previous number. Well, it's kind of you start at some point, you start to increment, but at some point you hit the maximum and you stay there. No matter how much you move forward in increments, you will stop at 4, and this is 0. Now, that would be a big problem, but notice the following. This kind of pathology, if you want, is not in contradiction with our axioms. The first axiom, the second axiom, and the third one. So we could have all the different number systems with similar problems. So that, for instance, numbers are not wrapping around, not wrapping back to zero, but back to something else. For instance, assume that 4 plus plus is 1. And in that case, 5 would be 1, 6 would be 2, etc. So, in order to avoid this kind of pathology, we must introduce what? Yet another axiom. And think about it. How should this axiom look like? Again, press pause if you want to think about it. And I will move forward. So we're back. We need to introduce another axiom, the axiom number 4. Different natural numbers must have different successors. So that if you have two natural numbers, for instance, I don't know, m and n, then if m is different than n, then m plus plus must be different than n plus plus. And if, which is a similar way of stating the same thing, if m plus plus is equal to n plus plus, then necessarily m equals n. So this axiom seems perfectly reasonable, so that you and I, again, can agree that I want to respect this. You know, mathematics is not completely detached from nature. We count things. We see objects in our room. I see a telephone, a laptop, my notes, an iPad, a lot of books, and I can count them 1, 2, 3, 4, 5, etc. So this is my environment. This is what I see around me, and I want to introduce a clean way of describing that environment, so that I can build upon it and move forward to investigate things which might be much more complex than just describing the number of objects that I have around me. This is why I am agreeing with you, and you are agreeing with me, on a number of axioms, rules, if you like, to define in a correct, accurate way what I see around me, the natural numbers. So, right now, we are in the position of proving that 6 is not equal to 2. Again, I'm going to leave this to you as an exercise, but a hint is to assume that it is equal to 2, and to run into a contradiction. So it looks like we are ready to go, but as a matter of fact, we are not. We could have strange elements in our number system which do not belong to the kind of numbers that we're trying to define, which are 0, 1, 2, 3, 4, etc. what if our number system consisted of integers and half integers, like 0, 1/2, 2, 3/2, sorry, etc. Well, that's a problem, because we need some axiom that makes sure, by the way, this is a 1 here, sorry about that. We want an axiom that is telling me to pick up the correct numbers, which are these, the integers, not the half integers. Now, but how do you do that? Again, of course, you understand what I am talking about, and of course, you know how to define the natural numbers. But that's a problem, because you have hardwired in your brain what the natural numbers are. And I am trying to get rid of that. I'm trying to get rid of that information. So this is an exercise that I am asking you to do. Try not to know anything a priori. We just have the information that I have introduced to you, that I have presented during these 36 minutes of time, nothing else. So how would you state in a mathematical language that we have to skip strange numbers like this, which we don't have any idea of what they are, because I have not introduced them to you? And in this case it is obvious, but what if after the natural number 22 billions, 33 millions, and 45, we had one of these, or a different kind of a strange number? We don't want that. And since we are not going to be counting by increments from 0 to infinite, we need to define a rule. And when I say a rule, you have to understand axiom, which avoids this kind of problem. And there is a very nice way to capture this kind of feature that we are introducing, which is the principle of mathematical induction. And it's going to be an axiom. And it goes like this. Let me clean the blackboard. And the principle of mathematical induction is very nice, because it is built on what we have defined until now, and it illustrates very well what are the fundamental properties that we need to introduce natural numbers. We need an element 0, which is the first natural number, and then we have to create a number system which is defined by jumping from one to the next one without wrapping up or resetting, etc. So we're now going to introduce the axiom number 5, which is the principle of mathematical induction. Now, again, this is an axiom, so it is something that we agree on. You and I are going to agree that it makes sense to introduce this kind of rule, because it's going to help us to avoid the kind of pathologies that I was mentioned before about the half integers. So consider any natural number n, n, n. So consider any property relative or pertaining to that natural number. A property P of n could be that n is even or odd or anything like that. Now, first, we're going to suppose that that property for the first element is true. And you see what is going on here. Here you see the nature, if you want, of the natural numbers. And then we suppose too that whenever P of n is true, then P of n plus plus is also true. In that case, P of n is true for every natural number n. So, again, the number 0 is a natural number. Then, we're going to assume that P of 0, the property we are interested on, is true for it, is true for 0. After that, since we can get to any natural number n from increments starting at 0, we assume that it is true for some k or n. Then we prove that it is true for k plus plus, and therefore we have proven that that property is true for all of the natural numbers. It makes sense, right? Because again, the skeleton or the characteristic of the natural numbers is built on 0 and the fact that n plus plus is a natural number if n is a natural number. So this axiom makes sense because if we can prove it for 0, we assume it for n, and we prove it for n plus plus, it must be true for every natural number n. And since you and I agree that it makes sense to assume this, the principle of mathematical induction is going to be an axiom. And at this point, I refer you to the proposition 2.1.11 in Tao's book, which goes like this. A certain property Pn is true for every natural number n. And the proof is simple, and it's just the skeleton of the line of thought that you have to use whenever you want to use the principle of mathematical induction to prove anything related to natural numbers. You first verify the base case 0. So you have to prove P of 0. Then you suppose that P of n has already been proven. Now you prove P of n plus plus, and when you do that, P of n will be true for natural numbers n, which is exactly the same thing I had said before. Now, let's move on. And it is time now to make an informal assumption. We're going to assume, and this is not going to be an axiom now, but it's going to be something built on the axioms, that there is a number system n whose elements are the natural numbers for which axioms 1, 2, 3, 4, and 5 are all true. So this is an assumption, but we're not going to prove it yet. And we will make it a little bit more precise after we have made our way through the set and the function theory. So it must be noted that I have been using the Arabic or Hindu-Arabic number system, 0, 1, 2, 3, etc. But would also have been using the Roman number system, and stealing a 0 from the previous number system, 0, 1, 2, 3, etc. And it would not make any difference, because there is a one-to-one relation between the members. We have an isomorphic relation. So we have a mapping between this world and this world over here. We have, of course, a one-to-one relation between 0 and 0, 1 and I, if you want, 2 and I, 3 and 3 times I. It's like, you know, a potato, or a potato like this is always a potato. It's going to be a potato in English. It's going to be a creïlla in Catalan. And it's going to be in pomme de terre in French. But you can see that it is, if you have a dictionary, so if you have a mapping, you will not be confused, and you will always be able to identify the English word potato with the German Kartoffel or the Catalan creïlla, because you have that dictionary, and that is an isomorphism. So we can move from one word to the other word by using that dictionary. So everything's fine. There's a very interesting thing about the natural numbers. Think about it. We have a set of natural numbers. I have not defined yet what a set is, but anyway, this is just kind of side note. It's like a bag containing all of the natural numbers. So 0, this one, for instance, 8, 5, 1, 2, etc. Now, each object, so each of the individual natural number, like 2 or 18,543, all of these numbers are finite, but the set itself is infinite. So the set is infinite, but it's consisting of individuals, objects, which are finite. So think about it. It's like having a bag of potatoes with an infinite number of potatoes, but each of the potatoes is finite. So the whole is greater than any of its parts. There are no infinite natural numbers, though. You can prove that by using axiom 5 and assuming that you have the notions of finite and infinite. So the natural numbers can approach infinity, but they will never actually reach it. Infinity is not one of the natural numbers, although there are other number systems which admit this kind of special numbers, like the p-adics, etc., and so on and so forth, but they do not obey the principle of induction, and therefore we will not consider them. And also please note that all of this is an axiomatic construct. So we're building the natural numbers in an axiomatic way, and not in a constructive way. And to my surprise, by reading Tao's book, I learned that we just very recently, in the late 19th century, discovered that numbers, and in particular natural numbers, can be understood abstractly via axioms without needing a concrete model, which solved a lot of problems. So now we're almost done with this first lecture, but before I finish, I want to tell you something else. You probably have not realized about it, but we can now define sequences in a recursive way. Imagine that you want to build a sequence A0, A1, A2 of numbers by first defining A0 to be some kind of base value. For instance, A0 is defined to be I don't know, A. This is like your base for some number, A, capital A. And then by letting the next one, A1, be some function of A1, so that A2 is defined to be F1 of A1, and so on and so forth, so that A of n plus plus is defined to be Fn acting on f of n. Now, this is very interesting because it allows us to propose recursive definitions, but note something. I've been talking about functions, but I have not defined what a function is. We will do that in the upcoming lectures, but a nice thing. So I am in some way abusing your attention and requirement of starting from a tabula rasa. But the nice thing is that while I am abusing my previous requirement, this is not going to be a circular problem, because when we formalize what a function is, or the concept of a function, we will not have to require the Peano axioms. But anyway, so recursive definitions. Suppose that for each natural number, so we have the set of natural numbers here, and we have a function which is mapping from the natural numbers to the natural numbers, f of n. Let's go like this. Let's see, because I was mentioning capital A before, but I prefer to stick to exactly what Tao is using in his book. Let's see be a natural number. So we can assign a unique natural number, an, to each of the natural numbers in a way that the first in the sequence is that C, and A of n plus plus is f of n acting on A of n. So for each natural number n. So we're mapping from the natural numbers onto the natural numbers via a function. And that's a very useful proposition which we can prove. And we can prove it via induction. So we want to make use now of an axiom, the axiom of mathematical induction, which was the axiom number 5. And remember how induction works. We first start from the case base, which is A0. And we have seen we're going to assume that this is true for this base case. So that function is mapping A0 with C. Now, you will not run into the problem of this function redefining the value of A0 because of axiom 3. That's a problem which we have now avoided thanks to our mutual agreement, the axioms. Now, so I said assume that this is true. No, we have seen that that this is already true. Okay, because we said before that we can assign this procedure gives a single value to A0, namely C. So we have now shown the base case. Now we want to suppose, by following induction, that this procedure is giving to you a single value for the case A of n. Therefore, we're going to have that an++ will have also a single value, which is going to be f of n acting on on A of n. Sorry. And none of the other definitions will redefine that value because of axiom 4. And therefore, we have proven the whole thing because we have completed the induction process so that the A of n is defined for every single natural number n which you can think of. And that will have a single value assigned to each A of n. And think about it. In order to arrive here, we have been using all the axioms that we have introduced. In a system which had some of the pathological problems that we were talking about before, that would not work because, for instance, some elements would constantly be reset. For instance, remember that previously we had been talking about of 3 being wrapping up to 0. So that there would be at least 2 conflicts for A0, either C or F3 acting on A3. And in the case of half integers, for instance, this number would never be defined. Now, this proposition, recursive definitions, are very interesting tool because later, as we will see it on the next video, we can define addition and multiplication. So that's it for today. Goodbye.